right, everybody. We're going to start talking about similarity today, and we're going to talk about similarity today, and I think also probably all of Monday, because this is just a hugely fundamental topic to geometry and to so much of the problem solving, the important and the harder aspects of problem solving in geometry. I've got a roadmap for similarity here up here, and each one of these could be its own class. And unfortunately, we don't have that much time. But 4 hours seems like reasonable coverage. So I encourage all of you, like if there's any one document from the summer program that I would urge you to read and read again sometime down the road, maybe in a few weeks or a few months, a second time over, it would be this one. And we're going to start today. Actually, let's talk about what similarity is. We were working on congruence on Monday, and congruence means you have objects that are identical insofar as all the sizes are the same. You could put one on top of the other and cover it up if two objects are congruent. That's not the case with similarity, but with similarity, it looks like you're looking at one object from further away than the other one. They have the exact same shape. It's just that the sizes are different. There's a scale factor involved. And that scale factor, sometimes we call it the similarity ratio, or if you ever see the phrase ratio of similitude, which is a little bit hard to see, to read at first, but older geometry texts may use that phrase, ratio of similitude. And so it's one to get used to. But that's what they mean. We're talking about proportions, and proportions are going to help us with all manner of problems. Now, one way to think about similarity is to think about what happens when you're standing near a tree, and there's the sun is overhead, and it comes down at an angle. The rays of the sun, the light hits you, and you cast a shadow, and the tree casts a shadow, and the proportion of the shadow to yourself is the same as the proportion of the shadow to the tree. And assuming you're standing upright and the tree is upright, you wind up with two similar triangles. And that's one good example of similarity. We're going to start by talking about AA similarity. Now, with congruence, all of our congruence theorems depended on three pieces of information. However, this very first, and usually we're going to use three pieces of information, but here we start with two. Before we even get started, why are we able to maybe just get away with two?
Mr. Crawford?
Yes.
I don't know whether you know this, but we can't see your screen.
Yeah, it doesn't show that you're screen sharing. Okay, now it does.
Should I start over?
No, I think
so. I do want everyone to see this screen right here. And you all have this document, right? I would suggest possibly to keep it open throughout the discussion. But I started out on this screen, and then here's you in the tree. Okay, let's talk about AA similarity. By the way, never assume that I've drawn my diagrams perfectly. I'm not that good of an artist. Let's mostly use just the information that just happens to be there from one diagram to another. Let's say that these two triangles both have a 50-degree angle and a 60-degree angle. And if we wanted to, we could measure all the sides. And what we would find, well, I'm going to give some labels here. AB, C and E, F, D, what we're going to find is that AB over D, E, actually AB over DF equals BC over FE equals CA over ED. So when we have similarity, we have these ratios, and this is that ratio of similitude or similarity ratio I was talking about earlier. And we could have done it bigger to smaller too, and that's fine. I think I have a habit of going smaller to larger, and sometimes it's good to have a habit just to frame yourself, to know what it is you mean with your variable. In this case, the variable r is less than 1. So how do we know that these two figures are similar?
They have the same shape.
They have the same shape. If we were to measure, assuming that my angles are correct, if we were to measure, we would have these ratios. So one is just a scale of the other. When we have two angles that are the same, what else do we have?
We have the third triangle since it's the triangle.
The third angles are determined. And so in a sense, AA similarity is A similarity. And that's where we have that 3 pieces of information like we had in all of our congruence theorems and what we're going to have later today in other similarity theorems. But we still haven't answered the question why. And I'm actually going to put that question off. We may do that at the end of class today. For right now, we're just going to take this for granted because that's a harder problem. And when we tackle that problem, we're going to take a deep breath and then go after it. So, okay, 2 angles or all 3 angles are enough to tell us that 2 triangles are similar. Is that true for quadrilaterals?
No.
I'd say no.
You need 3 angles to
Yeah,
find the
3.
fourth angle.
Okay, you would need 3 angles for a quadrilateral? What about all 4 angles? So, okay, if all the angles of 2 quadrilaterals are the same, are they similar?
Yeah.
Actually, no. To be honest, no. Because the square and the rectangle both have 90 and at all corners, but aren't similar. So I think it would rather be, okay, I'm not too sure, but I just know that having the angles wouldn't give you correct.
Right. These 2 objects are clearly not similar. There is no common ratio between the sides. We may have one pair of sides that are exactly the same, but one that is much longer in the rectangle. So no, just saying that the angles of a polygon are equal does not necessitate similarity, except with triangles. And let's jump into doing a little bit of problem solving with similar triangles. I'm going to show you one very common situation right here. So I'm going to redraw this here. I'm going to use length 5 and length 10 and length 12. And what we want to know is the length of MN. Okay, well, how can we identify equal angles?
We know that MN and OP are parallel, and P L is a transversal, meaning OPL would be equal to MNL. And with LO also being a transversal, we know that POL is equal to MNL. So knowing that all their angles are the same, we know that it's they are similar triangles.
Good. And I'll go ahead and say this. When I started doing geometry, I wasn't great at first at identifying where all the parallel, like I wasn't as good at seeing the transversals. And so it made it easier for me to extend lines. When we extend those lines, it's easier to recognize line LP, for instance, as a transversal, and line LO as another transversal. And so using those transversals, meeting those parallel lines, we get some pairs of equal angles. And of course, the angle at L is equal to itself. So we do have all three angles that are equal with two triangles. And here I'm going to write triangle. Actually, I'm going to do something wrong first, and I want somebody to tell me what's wrong when I write triangle LPO is similar to triangle LMN.
You wrote the letters in the wrong order.
Good. When we say that, when we write similar triangles like this, we're not just saying these two triangles can be arranged in some way to be similar. When we use this notation, we specifically mean that we are matching the angles that are equal to each other. Good. So now that we know that this is true, we know that we have similar ratios. So here's the way I like to do it. Once we've matched these corresponding vertices, that's helpful because we can go one pair at a time in the same places. LP over LM is equal to PO over NM and that's equal to LO over LM. So those ratios are the same. So we're interested in NM, which is the same as MN. That's the one we're interested in. What can we do?
PO is 12, so we can say 12 over NM is equal to LP over LM.
LP over LM, but we don't know LP or LO.
So we could use LO.
Yeah, it's the ratio on the right that we want because we know LO is 15 and we know LM is 5. And now we have an equation that we can solve with these two of the three ratios. And we can cross multiply and get 12 times 5 equals NM times 15. So what's NM?
4.
4. And that's our answer. Any questions or thoughts about this? And I'll go ahead and mention this. As you get good at this, you may look at this diagram and you may go, oh, well, it's just a 1-to-3 ratio. So 1/3 of 12 is 4. If you can already do that intuitively, that's fine. But I do think that it's important for you to be writing out these ratios and doing a little bit of deliberate problem solving because these problems absolutely will get hard enough that you just can't do it in your head. These problems, there will be problems at the International Math Olympiad that are similarity problems, and there's no way in the world those problems would be solved by most anyone without writing down the work in a detailed way and walking through all those relationships. So do get some practice. The problems will get harder and harder, and I think we'll see that even within a few problems here. Here's a second problem. Once again, we have a pair of parallel lines. And as I label, go ahead and think about what triangles are similar and in what orders we should be writing the vertices. And we're going to find the remaining lengths in this diagram. So somebody give me a pair of equal angles in this diagram. Shreya, can you give us a pair of equal angles? David?
PWX is equal to, sorry, angle PWX is equal to PZY.
Good. And you followed this transversal right here. Every now and then I'll have a student who says that PWX is the same as PYZ. That there's a tendency to want to just say, well, you have parallel lines, I'm going to look at the angles that are nearest each other, but it's not quite the case. It's those two angles that we marked right there. And then we have a second transversal, XY. And now that and that are alternate interior angles. And notice we also have the vertex angle right there. So we could use any two of those three angles to declare AA similarity. So we invoke AA similarity. Somebody tell me, in what order do we write the vertices?
One of three could be triangle PWX is similar to triangle PZY.
Good. And from this, we write out our ratios. Okay, so now let's fill in details that we have. See, PX equals 3, and PW equals 5. PZ is 10, and YZ or ZY is 12. And now we can equate the first two of these. And what is WX?
6.
And what is PY?
It's also
6.
6.
It is also 6. We have a ratio of similitude of 1/2, and we just do a little bit of equation solving and we're good. So now that we've gone through these first two problems, I want to point something out. These problems, they both were about parallel lines. I'm going to draw a pair of parallel lines here. Lots and lots of similarity revolves around parallel lines. And one of these situations was, hey, we have two crisscrossing transversals that meet outside of the pair of parallel lines. And thus we had equal angles there and there. Or we can have crisscrossing transversals that crisscross between the parallel lines. At which point we have that pair and that pair. And so one big leg up that you get is if you recognize parallel lines give equal angles and equal angles give similar triangles. and equal angles give similar triangles. Or sometimes, perfectly reasonable, we go from similar triangles to equal angles to parallel lines. And of course, on Monday, we did congruent triangles to equal angles to parallel lines. So you already have some practice with this. Now we're going to talk about another very common situation, similarity. We have a right triangle, and we have drawn the altitude from the right angle at B to the hypotenuse AC in right triangle ABC. And we'll call the foot of that altitude D. And I want to know what the other lengths in the triangle are, BC and DC. What are some equal angles in this diagram other than the right angles?
Angle DBC. Oh, continue.
Angle DAB is equal to angle DCB.
Those two may or may not be equal. It turns out that they're not. The angle at A is not the same as the angle at C. On the other hand, I'm going to mark the angle at A using a variable. And then we know that this angle right here is 90 degrees. So what is angle ABD?
It's equal to angle DCB.
What is it in terms of theta?
Will it be 180 minus 90 minus theta?
Okay, we can simplify that to 90 minus theta. And if that angle is 90 minus theta, what is angle DBC?
Theta.
Theta.
Yeah, we have those complementary angles that add up to 90. And what is the angle at C?
90 minus theta.
And so if it's harder to see, a little bit of angle chasing may help us. Now we can identify some equal angles, and I'm going to go ahead and mark them as we ordinarily do. Those two angles are equal. Those angles are equal. I'm not going to bother marking the right angles again. So now, somebody tell me, what is a pair of similar triangles in this diagram?
Triangle ABB is similar to triangle BDC.
Did you say BDC?
I said triangle ADB is similar to triangle BDC.
Okay, and I wrote ABD, so I switched those, so I'll have to switch the last two. Okay, good. You were correct, but I'm writing them differently.
Aren't they all also equal to triangle ABC?
Yeah.
Sorry, similar to.
Okay, slow down for me. Yes, that is correct. Triangle ABC is similar to, give me one of them in the correct order.
Triangle
DAB.
A. ADB. Yeah, ADB.
Good. Okay. Yes, all three triangles are similar. And of course, I just wrote these in a different way with the vertices in a different order. And every now and then, if I notice that there are three triangles in a diagram that are similar, if I've written them differently one place and then another, I might even go back and just rewrite them all in the same vertex order. Triangle ABC is similar to triangle ADB, and that is similar to triangle BDC. And we could directly say triangle ABC is similar to triangle BDC. So all these are perfectly correct statements. So now let's take a look. Where do we have information? Which triangle do we have the most information about?
Triangle ADB.
Yeah, we've got our most information there, so let's make use of that. For the first two triangles, ABC is is similar to ADB. We have AB over AD is equal to AC over AB, and that's equal to BC over DB. And we're looking for BC. So let's see, do we have enough information already? We do.
Yes,
What's
we
the
do,
length of
because
BC? What is BC equal to? I heard somebody, but we talked at the same time.
I think 6 and 2/3, I think.
Sure, and I usually don't even bother to rewrite a fraction as a mixed number unless there's some need for it. You know, writing it as a common fraction is perfectly fine. I'm not even going to process that extra step there. Okay, and then we want DC.
Will it be 16 over 3?
How do you know?
Because AD is 3 and BD is 4, and yes, so when you cross multiply, you get 16 over 3.
Perhaps, which two similar triangles are you using? I want to go ahead and just write out all the equations one way or another. We haven't really written out equations involving BDC. So let's use these two triangles right here. Early on, even if I can do this in my head or in some other way, I want to be as deliberate as possible in order to get practice seeing and making use of the equations that result. So we want DC, which is right here. BD is equal to 4. And then we look for other links we can make use of. AD is equal to 3 and BD is equal to 4. So 3/4 equals 4 over DC. And we can cross multiply. And I believe you did say 16/3, didn't you?
Yeah.
Very good. Okay, these first three problems that we've walked through are the most common problems you're going to see where you aren't just straight out given the angles, where you have a situation and you're looking for information first. You match up equal angles from parallel lines, or within a right triangle, when we drop down altitude to get another right angle, Then if we do a little angle chasing, we see where all the corresponding angles are. And we invoke AA similarity with 3 different triangles. Sometimes with right triangle problems, because there are 3 different triangles that are equal, you have to do a little bit more work matching up equations, but so far you all seem pretty good with that. Moving on. So we have 2 pairs of parallel lines in this diagram. And here we want to prove that EY over EX is equal to AD over DB. So this problem seems much more challenging to me. When I look at this, I don't quite as easily see everything, but I do see those 2 pairs of parallel lines. Can you identify which triangles are going to be similar? And if you need to, start marking angles. Draw this on your own and find which angles are equal. I see one here and here from those parallel lines. Archie, can you identify some other equal angles here?
Wait, I'm thinking.
Sometimes helps me to highlight parallel lines.
Is AED the same as ECB?
Good.
Yeah.
Nicely done. Harshita, can you identify a pair of parallel lines? Harshita, can you identify a pair of equal angles from that second set of parallel lines? Salorm?
VAE and then BAC.
Slow down for me. Say that again.
BAC and DAE.
BAC and DAE. Oh, it's true that those are equal. That's true. I'm looking at the second pair of parallel lines, though. We already have enough information for the 2 triangles that you mentioned to be similar, so I want to look elsewhere. So looking at the second pair of parallel lines, what angles do we get that are equal there?
May I try?
Go ahead, Stay. Hey, Snay, your microphone's breaking up. Snay, your microphone's breaking up. Go ahead and type it in Zoom group chat.
YEX. AYE
AYE, okay, I heard that.
and EXC.
Great. Salorm, do you want to finish? What is a second pair of?
Yeah. Well, there's YEA and XEC.
That's true. We have those vertical angles that are equal.
And then there's also YAE and then XCE.
Okay, yeah, we get those from the parallel lines. Good. And I'm actually going to erase out the vertical angles. Mostly because I want to highlight the finding of the angles from the parallel lines. Though there's nothing wrong with marking everything. When I mark everything, sometimes my diagrams get complicated enough that I don't necessarily see what I'm looking at as easily, but I think we're good here. I think we have a good amount of information. We can identify some similar triangles. Let's go ahead and identify a pair. I think maybe it was Salorm was on to something, but somebody identify a pair of similar triangles that we can see in this diagram.
Triangle AYE and CXE.
Good. And what's another pair?
Triangle ADE is similar to triangle XDE.
XDE, is that true?
Wait, no, sorry, EDX.
EDX, is that true? I don't know if we know that those are true. I see equal angles at D and E. Sorry, at D and B, and then equal angles at E and C. I'm going to write those down. I see that angle ADE is equal to angle ABC. And I also see that angle AED is equal to angle ACB. So triangle ADE is therefore similar to what triangle?
Triangle ACB.
Careful.
ABC.
ABC. Since we're writing this, it's important to get the vertices in correct matching order. And remember, that helps us out too. It helps us write our ratios most easily. AD is to AB. As DE is to BC. As AE is to AC. And with the first pair, we have AY is to CX, as YE is to XE, and AE to CE. Okay, now remember our goal. And it might be easier if we can see the whole screen at once here. Okay, remember our goal is to prove that EY over EX is AD over DB. How do we do that?
Well, we have to prove that the triangles that contain each of these sides are similar.
Maybe that's the case. Look at AD over DB. Those are actually just two segments along the same line. Well, that's a little bit weird, isn't it? They're not even in a triangle. Huh. Well, here's what I'm going to do. I'm going to take a look at one of this pair of ratios, and I'm going to look for it. And I spot it right here. Okay. Now I'm going to take a look at the other ratio, and I'm going to look for it in our information, and I spot it right here. But we have these in two different equation chains. Huh. Oh, excuse me. I apologize. I misread. AB down here is actually AD plus DB. So my apologies. I am slightly dyslexic, and I sometimes misread my own handwriting. So, okay, this isn't quite what we wanted, but it has a lot of what we wanted. It has a lot of, and over here, this ratio, AE over CE. Now we do see AE over here in the right-hand equation chain on the far right. Huh. But the denominator is not the same. What could we do?
Could we factor out the E?
Factor the E, what do you mean by that?
So that we'll be left with Y over X is equal to A over C.
Oh, that E is not a number being multiplied in. These are the names of segments. Segment YE over segment XE. And so when we name E, E is a vertex. It's not a number being multiplied in.
Then could we cross multiply them?
Perhaps we can cross multiply. That's a possibility, but I think mixing the links together, I don't think it's going to give us any new vision on the problem. When I look at the ratio AD over AB, I'm looking right here. This is the one that gives me pause, right? It wasn't exactly what we wanted. It wasn't AD over DB. We only got DB by looking at AB and saying, hey, look, DB is a part of that, right? DB was right here, and we were looking at this whole length AB. And we said, hey, we can rewrite AB as AD plus DB. And now we have what we want. We have that DB is in part of what we're trying to prove. Can we rewrite AE over AC in a similar way?
Yes. AC will be AE plus EC.
Good. Nice. Okay, let's do a little bit of equation manipulation. what can we do if we were to equate these two ratios right here? We know that those are equal, but they're not the easiest to work with, are they?
No.
What can we do? If you're not sure how to work with an equation, you might as well ask, how can I rewrite this? And here I just flipped the ratios, wrote the reciprocals. So long as we're not dividing by 0, we don't care. And here we can rewrite each of these as 1 plus another ratio. Okay, how does that help us?
Now I can put variables on one side of the equation, numbers on another.
Slow down for me, David. Say that again.
We could put the lines on one side and then the ones on another.
I think I understand what you're saying, but we could just subtract the ones away, right?
Yeah, of course, you end up getting 0 is equal to
Yeah.
EC over AE.
Right, and this is exactly what we wanted to see. EC over AE, well, that's the reciprocal of that right there. And XE over YE is equal to CE over EA. I'm just taking the reciprocal of those two ratios right there. So EC over EA is equal to XE over YE. And this is what we were trying to prove. DB over AD is XE over YE. Really, we would just have to flip those. We take the reciprocals and we're done. And just to be clear, I'm going to take a snapshot of this right here. And I'm going to drop it by where we ended up. So that you can see it. Any questions or thoughts about this one? So somebody give me a summary. Now that we've solved this problem, this is harder than most of the problems that we've worked this week. So tell me what all it is that we did along the way to solving this problem.
We were angle chasing.
We did a little bit of angle chasing, starting with what? What features of this diagram allowed us to do the bulk of that angle chasing?
The parallel lines.
Great, the parallel lines. Parallel lines gave us equal angles. This happened not once, but twice with two different pairs of parallel lines. We wrote down all the equations that we got. Then what?
And compare them.
Yeah, we looked at the equations and we compared the equations to the expressions in the statement that we were trying to prove. And it wasn't a direct match. We didn't quite see what we wanted. So we had to look and ask, how is it that we can rewrite stuff that's going on? And in particular, we rewrote stuff right here. And then that gave us something closer to what we needed, but we needed to do a little bit of mental gymnastics to say, hey, we need to rewrite something else, over here with AD to AB, that's the same as AE to AC, and then we could break up AC into EC and AE in the same way that AB was broken up into BD and AD. And then it was just a matter of equation solving. The algebra part was not the hardest part of the problem, though it is kind of an algebra that you need to get used to if you haven't experienced it as much. Okay, so great. We've worked through a few problems with AA similarity. Now let's talk about SAS similarity. So now, so far we've kind of skipped proving that AA similarity works, but we're actually going to give a good justification for SAS similarity. And this is going to take a little while right here. Okay, are these diagrams the same? Forgive my awful, awful art. Are these diagrams the same?
No.
Now, what's different?
One has parallel lines.
Okay, how do we know that the BD and CE are not parallel in the left-hand diagram?
Because it's not indicated.
Because it's not indicated. Okay, well that means that we shouldn't assume that they are parallel, but maybe we can prove that they're parallel.
Sure.
Okay, glad that you're open-minded to it. Good.
But I know, actually, I don't think we can.
You don't think we can?
No, we could. We could, my bad.
Yeah, we
'Cause
could.
I thought that the fact that there's a 2 and a 3 would make it like wouldn't allow it to be parallel, but then it's a triangle, so it doesn't really matter because, yeah.
Well, let's study these diagrams a little bit. Tell me about, what can we say in the diagram on the right?
So we can see that it has one of the side lengths is 10.
True.
The other side length is X.
Rishit, focus on angles for me. We have those parallel lines. What do parallel lines give us?
We can find some angles.
Wait, hold on, Snake. I want Rishit to answer this because I couldn't hear it in his voice yet.
Sure.
Rishit, what do parallel lines give us in general?
They give us like equal angles.
Yes, that's this wonderful, that They give us possibly a lot of things, but this wonderful piece of free information that we get from them is the equal angles. So Rishit, identify those equal angles for me.
ACE and I want to say AEC, but
ACE and AEC are not necessarily the same.
my bad. And ABX.
And ABX, good. That's right. Now use the other transversal.
AEC and AXB.
And AXB, good. Nicely done. Now I'm going to point out that the big triangle in these two pictures are, those are the same. These are two congruent triangles that we're starting out with. So I'm going to go ahead and mark those angles that way. But yeah, the parallel lines give us two pairs of equal angles. And from that, we can say, hey, triangle ABX is similar to triangle ACE. And we can go ahead and write our ratios. AB is to AC, as BX is to CE, is AX to AE. Okay. And we know AB over AC, by the way. We know that that is 8 over 10, which is 4 over 5. I'm just going to go ahead and write that there just in case that matters to us. Okay, so here's what I'm going to claim. I'm going to claim that point X is the same point as point D. And I'll go ahead and tell you that this is what we call a phantom point argument. This is where we have two diagrams, and we want a point or an object, line segment, anything, to function in one way in one diagram, but function in another way in the other diagram. We want it to have two different functions for us, and then we want to show that they're the same point so that we get both functions. In the right-hand diagram, the function of X was so that BX would be parallel to CE. That gave us parallel lines. Parallel lines gave us equal angles. Equal angles gave us similar triangles. On the left-hand side, however, the point D is being chosen with distances. D to E is 3, and D to A is 10. Sorry, I wrote 10, but I actually meant to write 12. Apologies. By the way, in the right-hand diagram, since the big triangles are supposed to be congruent, we'll call that 15. So now, let's take a look at the leftmost triangle once again. Oh, actually, no, let's go back to the rightmost triangle. Since AE is 15, what can we determine?
CE.
We can't determine CE.
You can determine AX.
What is AX, David?
AX would be 12.
Right. When we cross multiply, 5 times AX is 4 times 15. So AX is equal to 12.
Yeah, so that means that BD is parallel to CE in the left diagram.
Right. Here's what this demonstrates. In the left-hand diagram, what we have are two triangles in an SAS pattern. Here's what I mean by that. We know that already just from the diagram, AB over AC equals AD over AE. We knew that from the given information, and forgive me for writing 10 up there at first. That's the S and the S. And then we know the angle in between them is the same because it's the same angle. Angle BAD is equal to angle CAE. And that's the angle in between. Now, in the right-hand diagram, we know that we have these similar triangles. And in the left-hand diagram, since point X turned out to be in the same place as point D, that means that we have the same pair of similar triangles in the left-hand diagram. Triangle ABD is similar to triangle ACE. Sorry. Oop, I meant to replace that X with D. So whereas we used AA similarity over here, that actually established that SAS was a good enough pattern to demonstrate similarity. So SAS similarity does hold. Pardon me. Are there any questions about this one?
Bless you.
Thank you. Okay, let's take a look at a problem in which we can apply SAS similarity. And let's say that the perimeter of BCD is equal to 20. And we want to find the length BC.
Bless you.
Thanks. I'm going to give you all a moment to think about this one. Has anybody spotted any equal ratios?
Yes.
What do you see, David?
DC out of BC equals CB out of CA, which equals BD out of AB.
Wait, is that true? You said CD.
Shall I repeat?
What are the numbers in the ratios that you're using?
Asin.
I'm sorry, I couldn't understand.
What I said before was DC out of BC equals CB out of CA,
Why
which
do you say
equals,
that? When you say out of, do you mean over, like ratio?
sorry, yes.
Okay, why do you think that 5 over BC is BC over AC? I don't think
Could you
that's
please repeat the
true.
question?
I don't think that it's true that DC over CB is BC over CA. Why do you think that's true? Is there a reason why? I think I know what you're doing. I think that you've seen that happen in right triangles. And there's a reason why it happens in right triangles, and we'll cover that at some point. But that's not necessarily true in this diagram. Okay, now I'm going to throw out a hint.
Okay.
Length AD is 9. Why is that a hint? Does somebody here spot a pair of similar triangles?
Well, if we take ABD as a whole triangle, we realize that the other triangles are just parts of it. So we can see CD over AD is equivalent to AC over AD.
Five over 9 is 4 over 9?
Oh, I'm sorry. I think I'm confusing myself. But they are both part of the same original shape.
I don't know if that's true. In this problem, it's tough to see what we're looking for. Sometimes you just have to write it down and see it in the numbers. Sometimes your number sense is going to matter. Usually when we think of number sense, we think of number theory. And but every now and then in geometry, it helps us too. Look at the numbers in the diagram. Remember, we're trying to use SAS. Well, if we're going to use SAS, we need an angle, but we need sides in ratio lengths. Can anybody spot in the numbers two ratios that are the same?
I'm not sure, but 4 times 1.5 is 6, and 6 times 1.5 is also is 9.
Right. 4 over 6 is 6 over 9. That's AC over AD, no, sorry, over AB equals AB over AD. So somebody tell me, that combined with what angle gives us two similar triangles? Of course, we can just look at the vertices. That tells us we want to look at triangle ABC. And then we can look at the vertices down here. It tells us we want to look at ABD, the big triangle. What angle do they share?
Angle ABD.
Yeah, triangle A, and we could put it this way. We could say triangle, or sorry, angle BAC is equal to angle DAB. I could have said BAD, but I wanted to write it in the same order in which we're going to write the sides. By SAS similarity, we have triangle ABC is similar to triangle. Somebody give me the right order of vertices.
Is it ACB?
ABD.
It's not ABD.
BBC.
ABC and look at this ratio right here.
Is it ADB?
ADB. Right. That's where those ratios were. Okay. So now that we've established that those triangles are similar, now we have AB over AC equals AD over, sorry, AB over AD equals AC over AB equals BC over DB. Well, wait a minute. We can't determine BC and DB yet, can we? What do we know about BC and BD at this point?
We know that BD is equal to BA because the triangles are similar.
We don't know that BD is equal to BA or AC or anything like that. What we have are ratios. And remember, we know the ratio of similitude. AB to AD is equal to 2/3. That's 6/9. So BC over DB must be that same ratio. If we wanted, we could rewrite BC as 2/3 of BD. And now let's remember, we have one piece of unused information in this problem.
Okay, so that would make DB 5.
So what is BD equal to?
10.
Close.
9.
It's 9, yeah. 5/3 of BD equals 15, so 3/5 of 15 is equal to 9. So this is 9, and 2/3 of BD is 6. And 6 is our answer. Any questions or thoughts about this one? I'll go ahead and say this is a challenging problem. It doesn't look like a problem that's going to be as hard as it turns out to be. When looking around, it takes some time to get used to the fact that you might have to put numbers together to get ratios to see to make use of in order to make SAS similarity. But you will develop that skill over time as you see a few problems and get used to those circumstances. Okay. Now we're going to talk about a third similarity theorem. We've used AA, which is really AAA, 3 pieces of information. Then, so that's no sides, just angles. Now we used 2 sides and an angle. And next we're going to use 3 sides. And this is where we just have all 3 ratios present. And I'm just going to jump into a problem here. Okay, C is going to be the midpoint of AD. And now here's what we want to prove. We want to prove that AE and BC are parallel. And we want to prove that AB is parallel to DE. What tools do we have with which to prove lines are parallel?
Well, we have the SSS similarity, which we can use to prove that these are similar triangles, so they will have the same types of angles. And if we find that midpoint, is it the midpoint was labeled as what again? Sorry.
Oh, that's C. Oh, excuse me. I didn't write that down, did I?
Yes, so if the angle ACB is equivalent to angle EAD.
Oh, slow down, slow. I wanted to start with just generalities, but I can see that you're going in exactly the right direction. What Theorem is doing is he wants to use equal angles to establish the parallel lines. That's right. That's really the only thing that we've discussed this week as a method for demonstrating that 2 lines are parallel. So we want equal angles. Well, we get equal angles from similar triangles, but we don't have any angle information. So if we want similar triangles, the only tool at our disposal is SSS similarity. So this is an example of thinking backward in geometry or thinking backward in mathematics to ask, what is it that we want? And then can we work toward that thing that we want? Can we move forward toward it? So backward and forward together. So somebody tell me, where do we see a pair of similar triangles? Or where do we see equal ratios?
Well, a pair of similar triangles would be triangle ACD and triangle ABC, and it can be seen
Okay,
in
slow down for me just a moment. Let me write those down. I don't remember perfectly when I hear that much information. You're saying triangle ABC is similar to which
triangle
one?
ADE. Triangle ADE.
ADE. Okay, so AB is 5, AD is 8. So you're saying that's equal to, let's see, AC is 4, and AE is 12.
No, I think I say. Yeah,
but
I
if
think
you
it's
see
actually
clearly
supposed
enough,
to be. Manvendra can speak.
okay, I should say something. Okay, so if we can also see that like the sides in ABC, the sides are 5, 6, and 4, and the sides for AED are 12, 10, and 4, and then 12, 10, and 4, their halves are 5, 6, and 12, 10, and 8. Their halves are 5, 6, and 4. So they are basically double.
Okay, great job, Manvendra. Manvendra has looked for a way to put together the numbers to make equal ratios. And so now we go about replacing what we see in the numerators and denominators with letters. So AB over AD. And then the 6 came from, well, that was BC. The 12 came from EA. And then finally, we had 4 was AC, and the 8 was AD. So ABC is similar to, how do we say it, Manvendra?
Please, can you repeat what you said?
Yeah, triangle ABC is similar to what triangle by your observations?
Triangle ABC is similar to triangle ABC. Triangle ADE.
We wouldn't say it that way. That does not match the corresponding sides and vertices.
Could
Maybe
I try?
triangle DEA.
DEA. Good, whoever said that. Okay, ABC is similar to DEA. And because those triangles are similar, we can start matching angles. The angle at A is going to be the same as the angle at D. Oops, excuse me, I marked that incorrectly. Angle A in triangle ABC is equal to angle D in triangle DEA. And then angle B in ABC is the same as triangle E in DEA. And then the angle C in triangle ABC is the same as the angle at A in triangle DAE. Now, how do we know that AE is parallel to BC?
Because since
we know this because of the fact that if we use the alternate angle theorem, we can see that the angle at A is the same as the angle at C, and that can only happen with parallel lines.
Not the angle at C, but the angle at D. A and D have angles that are the same around that green transversal. Good. And now with the other pair of parallel lines, AB and ED.
If you extend line BC to touch line ED, you can tell that angle ABC and angle AED are the same due to alternate interior angle.
Good. Wait a minute. I said good, but I may have lost track of what you just said.
Okay, I see what you meant. If you extend line BC to touch line ED, yes, you see that E is correspondent to the angle inside, I don't know, let's say beside angle ADE, inside the smaller triangle formed there.
Okay, so you're using the fact that those two lines are parallel.
Yes.
Okay, great. Now we can transfer the angle at E over here like that.
Yes.
Okay.
So then you know that they are equal since they are alternate interior angles.
This one and that one?
Yes, the one on top and the one at the bottom. I'm
Good,
not so
very
good at my wording, forgive me.
Yeah, and now we know that those two lines are parallel from that transversal and those two equal angles. Good. Nicely done. And there are a number of ways that we could have gone about the end game there. I like the extending the line right there. That shows that you're seeing the whole line. There's no reason not to, even if we haven't drawn it all. Very good.
So I have a question.
Yes.
Would it be necessary to find the values for all the sides to prove that the lines are parallel?
That's a tough question to answer. You know, for any particular problem, you have the information that you have, and then you have a set of possible theorems that you can apply. And if you can make the information match your theorems, then you have new information. And so there's no like one grand answer to that. If I understand what you asked, there's no one grand answer. You just have to, you know, go about it one problem at a time with the information.
Okay.
And if I haven't answered your question as completely, ask it again at the end of class. Maybe the next few problems that we go through will help out. We're going to give this some practice. We're going to see a number of different problems, different kinds of problems where we make use of similarity now. And DE in this diagram is parallel to BC. We're going to find the lengths of, or we're going to find the values of all the variables. So what is our focus in this diagram? What is the piece of information that does the most for us?
The parallel lines.
Okay. What is a pair of useful similar triangles that we see?
Triangle DF and BFC.
Okay, say that to me once again. Did you say DEF?
Yes.
And that's similar to which triangle?
It's similar to triangle BCF.
So not quite. Let's go about marking our angles. That one and that one are alternate interior. That one and that one are alternate interior. Now by AA similarity, DEF is the same as
Is that CBF?
CBF, right? It's not BCF, it's CBF. And that labels the vertices in the right order. And that means that we can go ahead and just write out ratios. DE is to CB, as EF is to BF. And DE is to CF. Okay, and we have a bunch of information there.
It's DF is to CF, rather.
Oh, and the last one, you're right. Thank you. Okay, so we have some of this information. Let's see, DE is 45. So 45 over X equals 36 over 64. So we have our similarity ratio is reduces to 9 over 16. So what is X? Sanjana, what is X? Non-Norley, what's X?
Would it be 85?
Not 85, you're very close.
Please, can I try?
Sure.
90.
It's not 90.
No, 80.
It's 80, right? If we cross multiply from those two ratios, or we could say it's 9 to 16, and 45 is 5 times 9, so what we want is 5 times 16. Okay, what is Y?
$57.
Not 57. 9 over 16. 27 is 3 times 9.
48.
48. Okay. So we can't get Z yet, however, from these triangles. So can we identify a second pair of similar triangles here? Sanjana, can you see a second pair of similar triangles in this diagram?
I'm sorry, I keep getting disconnected. I'm trying to figure it out.
Okay. How about Harshita? Harshita, can you identify a second pair of similar triangles here? Anyone else?
Yeah. Triangles BDF and ECF.
Maybe. I don't know. I can see one pair of similar angles.
Could I try?
Remember from earlier, I'm going to go back to this. This is the thing to train into your brain, is a pair of parallel lines in black. We either have crisscrossing transversals inside or crisscrossing transversals outside. And those give us those AA similarity patterns. Here, we've already identified crisscrossing transversals inside. Now, what else do we see?
Should I just give the triangles?
All right, go ahead, David.
Triangle ADE is similar to triangle ABC.
Good. And that comes from this angle right here is the same as that angle right there due to the parallel lines. And then that angle right there is the same as that angle right there. And now we have a second pair of similar triangles. So take a look at our ratios. And where is Z? Z is AE. And it is also part of AC. Do we know the similarity ratio? Hey, wow, the similarity ratio is exactly the same ratio as before. Right, the proportion of ADE to ABC is the same as the proportion of DEF to CBF. That's interesting to observe. Okay, so how do we find Z?
And we could flip the equation.
We could. What else could we do?
Cross multiply.
Cross multiply. I think it's probably good to just dive right into the algebra, cross multiply. Oops. I'm going to check that answer to make sure it's correct, since we had a little bit more arithmetic going on there, and it is. Notice what I did at the end there. What did I do that made my work easier?
You didn't multiply.
Good. I'm glad you noticed. Yeah, as often as possible, I save my arithmetic until the end. And when I was young, I didn't do that. When I was young, the moment I saw 45 times 60, I would have been multiplying it together, and I would have come up with, okay, that's 2,700. And then I would have wound up dividing 35 into 2,700. Maybe I'll cancel in, maybe I'll come up with a mixed fraction. But really and truly, life is just easier if you save all your arithmetic until the end and see what cancels out and what work you might not need to have done. But this is a good problem. It involved the crisscrossing transversals both inside and outside the parallel lines. Moving to the next one. Let's see. Here we're going to have a right triangle, and we're going to embed a square. The biggest square that we can fit that shares the right angle with the triangle. So the legs of the right triangle are 6 and 10. And we want to find the side length of the square. I'm going to let you all think about this one for a couple of minutes here. Okay, so let's talk about where we might find similar triangles. We have right angles all over the place. So I'm going to point out that triangle ABC is similar to triangle DBE, and also they're both similar to triangle FEC. Well, let's focus on what it is that we need in this problem. We need the side length of the square. S, 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 S. But look, 10 minus S, 6 minus S. We have all these different places where we have S. And we want to pick two triangles to compare them. So which two triangles should we pick out of these three? We could write down all the different ratios. Which one of these triangles has the best information to make use of?
I think triangle FEC.
FEC? We can use triangle FEC, but that's not the one that's most important to us.
I think we could use ABC.
Why ABC?
Maybe because it has the whole square in it.
Not because it has the whole square in it.
Because we are sure of the side lengths of two sides.
Of the side lengths, right. We have solid information. So let's make use of that. And really, we can use either of the other two triangles. I'll go ahead and just use these two since they're next to each other. AB over DB equals AC over DE equals BC over BE. And we know that AB is 6. We know that AC is 10. We're going to use those first two ratios. I'm not even going to bother with the others. DB is 6 minus S, and DE is S. So 6 over 6 minus S equals 10 over S. What do we do now?
Cross multiply.
Cross multiply. 6 times S equals 10 times 6 minus S. And that's our answer. So big picture, a lot of times with these right triangle similarity problems, when we bet a square or we drop an altitude, if we somehow create similar triangles, we wind up with several options. And we just ask ourselves, well, which of these options is going to be the best for us, the most useful? And the most useful in this case turns out to be ABC, because it's just the one where we have the most given information. And we could have given different types of information in this problem or asked for something else, but that's the one that we reached for. Okay. Now here's something that we've already talked about very briefly once today, which is what happens when we drop an altitude in a right triangle. And I'm going to go ahead and label some things here. So let's begin by identifying similar triangles. And remember, you write this on your own paper if you need to. Write down like a variable like theta or x to represent an angle and chase that angle around the diagram. Make sure that you match up the angles correctly that you need. Somebody tell me what similar triangles we can identify.
The QPX is similar to PRX.
Good. That's correct. I'm going to start with a different one, though. I'm going to start with the big one. And David, that was you, right?
No, Wasalam.
Oh, sorry, Celarm. Celarm, tell me tell me the orders of the vertices that we're going to use for the two triangles that you mentioned.
It was QPX was similar to PRX.
Yeah, tell me, however, in the order of the big triangle named.
So the angle at Q would have matched the angle at P. The angle at P in the other triangle would have matched the angle at R, and then angle at X would have matched to the angle at X.
So PQR is similar to?
No, I didn't say PQR was similar to another triangle. I said
I know that you mentioned two other triangles, but what I'm asking you to do is name those two triangles in the order that makes their angles the same as PQR, because all three of these are going to be similar. Right, we saw that in a similar diagram earlier.
Yeah.
I'll name the next one. You'll understand what I mean after I name this. PQR, in the big triangle, P is the right angle. So I'm going to go XQP. Do you see what I was asking now?
Yeah, because they have a right angle at. I couldn't see how they were similar yet, so I was trying to figure it out in my head.
Got it. Okay, and now name the last one in the correct order.
XPR.
Okay, so now we have these similar triangles. Let's write out all the information that we get. And this is going to be a big moment right here. something is gonna pop out of this that is momentous. So let's see. P, Q, actually I'll go ahead and write it in terms of A, B, C, D, E, and H. Let's see, in the big, let's see, P, Q, R, P, Q is A over D Okay, that's from the first two triangles. Now from the first and the third.
But line QR is actually C, not D.
I'm sorry, what are you asking me to look at?
You said it's from the first two triangles. I get that PQ is A, but you wrote A over D, and D is rather PR, not QR.
D is QX.
Oh, sorry, my bad.
So A in the first and third triangle, A over H is, let's see, PR over XR. And now the second and third triangles. Okay, I hope I've written all that correctly. So now here's a time we're going to go hunting for interesting information. And we're going to find multiple pieces of interesting information. Now, the first one I'm going to point out just comes right here. If we cross multiply those equations, we find out that H squared equals D times E. And what that means is that H is the geometric mean of those two pieces into which the altitude cut the hypotenuse of the big right triangle. That's kind of cool. We can physically see the geometric mean is the altitude to the hypotenuse, is the geometric mean of those two pieces. Okay, what else do we see? Well, that was interesting because we had two equations that had H, right? And that turned out to give us a nice little theorem. So we see two variables in these equations two more times. We see these two ratios right here. Those two give us, when we cross multiply, A squared equals CD. Do we see that again somewhere? We do.
Yeah.
B squared equals CE. Okay, well, that's interesting. What can we do with these two equations?
To find the square root.
We could take the square root. Nothing wrong with that. But that's not what we're going to do. What are D and E?
The sum of D and E is C.
Yes, the sum are C. If we take these two equations and we add them, we get A squared plus B squared equals CD plus CE. And we can factor out a C, and we get D plus E. What did we just do?
You just change the equation so that it's now A squared plus B squared equals C squared. And when you find the root of that, it's A plus B equals C.
A squared plus B squared equals C squared. We just used similar right triangles to prove the Pythagorean theorem. And that's beautiful. And that seems like a good note to end class on. Are there any questions or comments about this problem or anything that we've done today?
Yeah, I just wanted to find out a bit more about geometric mean. You mentioned that when you were talking about H. I'm not really sure.
Yeah, there are different kinds of means, and a lot of them have geometric interpretations. There's an arithmetic mean would be where we take two numbers and add them and divide by 2. There's the geometric mean, where we take two numbers, multiply them, and take their square root. There is a harmonic mean, where we take the reciprocal of the average of the reciprocals. And there is a quadratic mean, which is the square root of the average of the squares. And it turns out that all of these pop out at in different places geometrically. This might be a longer conversation, maybe worth looking up, but going back to this diagram up here, in red, we have a geometric mean. It turns out, and I won't explain this completely right now, we'll talk about it maybe in a future class, but if we identify the midpoint of that hypotenuse, well, it turns out that PM, QM, and RM all have the same length. And that length is equal to the average of D and E. So it's D plus E over 2. So you can see those two red lengths from P. The shorter one is the geometric mean, and the longer one is the arithmetic mean. If it's an isosceles right triangle, they're the same. So these means show up all over geometry, and we will see them again. Any other questions or thoughts?
Yeah, Mr. Crawford, please, if you want to prove that a certain triangle is an obtuse triangle, which similarity will we use?
I'm sorry, can you repeat the question?
Sure, I'll say if you want to prove that a certain triangle is an obtuse triangle, which
I heard if you want to prove a certain triangle is, and then both times I couldn't understand what you said after that.
Is an obtuse triangle.
is an obtuse triangle, just a triangle with an angle greater than 90.
Yeah, which similarity would you use to prove it?
All the different similarity theorems are still available. And nothing that we did today has anything to do with whether or not a triangle is acute, right, or obtuse. There is a right triangle similarity theorem, and there's a right triangle congruence theorem, and those are the ones that we haven't covered yet. And we'll get to that down the road in the future.
Okay, thanks.
You're welcome. All right, well, practice out problems in the document that I sent you, and I hope you all enjoy the test tomorrow.
Thank you, Mr. Crawford.
You're welcome. You're Friday.
Thank you, Mr. Crawford.
Okay, yes, bye.